this last presentation is probably one of the most challenging ones for me to give, because it's the last thing that separates us from the party tonight. So I guess that everyone wants to head out, so I will try to go this as quick as possible. So this presentation is about recent advances in IPv6 security. Before actually getting into the talk, I'd like to thank the BruCON organizers and the locals. I have been having a great time here. Very nice city. My first time to Belgium, so thank you to all of that. Okay. Okay. A brief introduction about myself. I work as a security research and consultant for SI6 networks. I've been involved in the last 8 years or so on different projects for 2 organizations in the UK government. I'm also very active at the IETF, which is the standards organization that standardizes the internet protocols. And here's the URL of my personal website, where you can access many of the documents that we will be going through during this presentation. This is the agenda of this presentation. Essentially, we will start with a motivation disclaimer, and we'll go through several topics that have to do with IPv6 security. This presentation is like a snapshot of the latest advances that we have been doing in terms of IPv6 security. So it's not necessarily that all of them are related between each other, but again, there are different topics on which we have been trying to make progress. Okay. So, disclaimer about this presentation. First of all, it assumes that you know the basics about IPv6 security, and that you know the basics about IPv6 security too. So, there's almost not going to be any kind of IPv6 primer or introduction. It's also the case that much of this stuff is still work in progress. So, there are much of the stuff that we will be talking about are documented in IETF Internet Draft. So if you have any input to that work, even during the presentation or after the presentation, that will be welcome. Last disclaimer is that there are not going to be any zero days, and the reason for which I'm saying this out loud at the beginning of the presentation is that sometimes in security conferences, people are like waiting during the whole presentation for the 0 day, and I have been at a few conferences when people got frustrated at the end of the conferences because there was no 0 day. So it's in the display already. So first of all, let's start with the motivation for this presentation. You probably have heard about V6 already. Essentially, it's a protocol that tries to address the problem of IPv4 address exhaustion. If you think about it, most of the general purpose operating systems already support it. And truth is that whether you like it or not, and sooner or later, you will end up deploying it. Actually, you might argue that most of the networks that we have nowadays have at least partial support have a partial deployment of V6, because many of the devices that you have on those networks are IPv6 enabled. IPv6 represents a number of challenges, not only from the networking point of view, but also from a security point of view. Essentially, it's a new technology. We don't have much experience about it. There's not much support in security devices, etc., etc. So this presentation will try to summarize the attitude that you usually find in the operations and security community when it comes to IPv6 security challenges. So option 1 that you usually find out there is that people essentially ignore the security implications of IPv6. Sometimes it's because they explicitly want to do so. In other cases, it's because, for example, there are not that many best practices available. So I know of cases in which the network guys were trying to do the right thing, but then they talk to the security guys, and they do not provide any kind of security best practices for them. Option 2 of the attitude of the things that you see out there is this one, in which essentially people are more conscious about IPv6 security issues, and they say, well, there are all these things that we should address, we don't really know how to do it, and they take the second attitude. Sometimes option 2 is a consequence of option 1. So the idea of this presentation is that we want to avoid the first and the second option and go through this one, which is essentially about discussing some of the IPv6 security drawbacks, but for the most part not just discuss the problems, but also try to find ways to address these problems. I know that many times in the security community it pays more to actually discover problems In this case, we will be discussing some of the problems, but for the most part, the idea is that we want to address those problems. So, much of the materials that I will be presenting today are the result of a project that we carried out during 4 or 5 years or so. Essentially, what we did was analyze all of the IPv6 specifications. We also analyzed some open source implementations of IPv6. And in those cases in which we identify problems, either in the specs or in actual implementations, we came up with proposals on how to mitigate those issues. In many cases, we tried to cooperate with vendors. In some cases, we succeeded. In many others, you could act that we failed or that they didn't care. In any case, we will be talking about all this stuff. And as I said before, much of the work that we did was taken to the IETF, and we hope that where necessary, our work will result in specification updates. So let's talk a little bit about IPv6 addressing. Essentially, the main driver for IPv6 deployment is the increased address space. Even when you hear things such as improved quality of service, security, or whatever that is, true is that people that deploy v6 do it because it has an increased address space. And essentially, the v6 addresses are the same as with before. For example, if you take a look at the host, the addresses are aggregated into prefixes for purpose of routing. We also have different address types, in the sense that we have unicast, multicast addresses, and so on. Different address codes too, local, global, and so on. Same thing as with before. And probably one of the few differences between v6 and before is that in the typical case, every IPv6 interface has more than one IPv6 address configured, as opposed to the before case, in which, except in those cases in which you have aliases, you have a single address. So this is, even when, of course, there are many combinations of global, when it comes to the scope and the type of addresses, we will just discuss the global unicast addresses, which are the ones that you will be using for connecting to remote hosts, remote services. This is the syntax of global unicast addresses, in which, as I said before, it's essentially the same thing as before. You have a global routing prefix, which is the prefix that you get from your upstream. Then a few bits for subnetting, same thing you do with before. And then you have an interface ID, which is essentially the same thing that you had in before, with the only difference that in before you call that a host ID, and in v6 it's an interface ID. Probably the only difference when it comes to the addresses is that since the typical interface ID in IPv6 is 64-bit long, you have many options as to how to set that interface ID. The most typical way to do it is to include the MAC address in the interface ID, modulo some bits that you need to flip and a couple of bytes that you need to insert in the MAC address. There are other options, for example, such as privacy addresses that we will discuss in more detail later. Essentially, privacy addresses randomize the interface ID. You can also manually configure the address, and of course that means also the interface ID. You could, for example, set the interface ID to all zeros and just vary the last byte. And there are some transition and coexistence technologies that mandate how you create those addresses. So this is the only intro that we will have for v6 addresses. And the idea is to now try to analyze what are the implications of v6 addresses when compared to before addresses. So first of all, let's analyze what are the implications of v6 addresses on address scanning attacks. Of course, address scanning essentially means the same type of host scanning that you usually do by sweeping an entire address space and the like. So the usual myth that you hear about IPv6 host scanning is that an IPv6 host scanning attack takes ages. And actually, I didn't come up with this quote. Actually, when preparing the slideware, I went to Google and tried to find someone saying this kind of thing. The numbers vary from something along the lines of, 500 million years to maybe 5,000 million years or whatever. The thing is that most people deem IPv6 address scanning attacks as unfeasible. And what we are going to do now is try to think a little bit more about this topic and try to come out with some conclusion as to whether those attacks are really feasible or not. I think that the most elemental question to answer here, to have an answer on this topic, is what is actually the CERT space when you are trying to scan a remote network. So the question is whether when you are scanning a remote network, the CERT space is really 64 bits or not. Most of the people that come up with numbers such as 500 million years or the like, they assume that the IPv6 subnets are 64-bit long. That you have 64 bits for selecting the address or for selecting the host ID, and they kind of also assume that the addresses of the hosts are randomly spread over that number of bits. So when I was studying this stuff, I tried to find out whether anyone had bothered to actually measure how IPv6 addresses are generated or selected. There was this paper from David Malone published earlier in 2008. Essentially what this guy did, he tried to measure how are the addresses of hosts, how are the addresses of routers selected. For measuring the addresses of hosts, he essentially set up, I don't recall if it was a web server or an FTP server, but he just logged those addresses and then tried to categorize the addresses into the different categories that we can see in this table. Then on the right-hand side, we see similar type of measurement, but for router addresses. I think that in this case, what he did, he ran traceroute against different destinations, and that's how he got the addresses of routers. One of the things that we can see from the two tables is that IPv6 addresses do follow patterns. For example, in the case of host, we can see that at least 50% of the addresses are based on Slack, which is another way of saying that they include the MAC address in the interface ID. Then we have 20% of addresses that essentially encode an IPv4 address in the interface ID. And when it comes to routers, 70% of the addresses are low byte, which means that they are manually configured and the interface ID is set to all zeros and you just vary the last byte. That's typically the thing that you do when you're manually configuring an address, because of course you're not going to set like 64 bits randomly, but you just set it to all zeros and just vary the last one so that it's easier to remember. Other than the numbers themselves, other than the actual numbers, which I would say that they have probably varied quite a lot since 2007 or 2006 when all this work was carried out, I think that probably the most important result from this paper was that it shows very clearly that IPv6 addresses do follow specific patterns. This is the syntax of the interface IDs when they embed MAC addresses. Essentially, MAC addresses are 6-byte long addresses. So when you want to generate an interface ID out of the MAC address, what you do is you split the MAC address into two halves and you insert the 2 bytes FF and FE in the middle. That's essentially what you do, modulo for tweaking, for flipping a byte in the IEEE OUI. So what can we say about these interface IDs? Well, first of all, of course, since the middle 2 bytes are fixed, you wouldn't include those 16 bits in the CERT space because they are constant. Now, when it comes to the upper 24 bits, the IEEE OUI is a number that identifies the manufacturer of the network interface card. So you could argue that if, for example, you wanted to scan a specific network and you know, for example, what's the manufacturer of the network interface cards that are in use in that network, then you will probably have not many more than maybe 5 options, 5 different numbers for the upper 24 bits. You simply go to IEEE's website and they provide, it's publicly available, the database of which vendors have been assigned which IEEE OUIs. Now when it comes to the lower 24 bits, in principle you might argue that those 24 bits are kind of like random. So even if we consider those bits to be random, the search space would be around 24 bits, which already make the search space feasible. Now, if you think a little bit more about the low order 24 bits, Actually, they are not really random because manufacturers typically assign them sequentially. So that means that, for example, you have this distributor of some vendor and they buy a bunch of systems manufactured by the same vendor, then you will find that the MAC addresses are consecutive. Okay, so that means that if some network has a bunch of systems from the same vendor that have been installed at the same time, chances are that if you find one system that is alive, the other one will have consecutive MAC addresses, and that's something that you can benefit from. Also, we have done some roam measurements, and the lower 24 bits of MAC addresses tend to be geographically clustered because there is some distributor that buys this bunch of systems, and they, of course, they sell those systems within the same region. So that means that if, for example, you find that this company has this range of MAC addresses, well, if there is another company that bought the same brand of system probably at the same time, you will find that that their MAC address space is clustered too. So typically, worst case scenario, we will have a search space of 24 bits. And bottom line here is that when we have gone down from a search space of 64 bits, that's what's typically assumed, to 24 bits, which is a number that is feasible. Something that is maybe even more interesting and that might shed some light with all the virtualization hit nowadays. If you look, for example, at virtualization technologies such as VirtualBox, they select the MAC addresses for the virtual interfaces from a fixed OUI, which means that if you are targeting virtual machines, you don't need to even guess or look up in IEEE's website what's the corresponding IEEE OUI, but it's fixed. So in that case, the search space is, in the worst case, 24 bits long. A similar thing happens with VMware. It's just that the IEEE OUI changes. For VirtualBox, it was 08, 07, 27, whereas in the case of VMware, it's 00, 05, and 59. Actually, when it comes to VMware, the search space is actually reduced because they set the low order 24 bits, not randomly, but some of those bits are fixed. For example, they are set as a result of the IPv4 address of the host system. So the thing is that if you are targeting virtual machines, then the search space is, in the worst case scenario, 24 bits. Again, something completely different from the original 64 bits that are typically assumed. If we look at other address types, I mentioned that there are addresses that embed IPv4 addresses. The IPv6 address rotation allows you to write addresses in this way, okay? So essentially for the interface ID, you can just write an IPv4 address, and that is of course useful, for example, if you are operating infrastructure requirements such as routers, you might set the interface ID in this way so that it's trivial to remember the V6 address as opposed to having to remember, for example, the MAC address of the corresponding network interface card. If we assume that addresses are selected in this way, the search space is of course the same one as the IPv4 search space, and if we assume that the network there is, for example, it's a /24, well, the search space could be something along the lines of 8 bits or worst case scenario 16 bits. Other addresses, I mentioned IPv6 low byte addresses, and I'm using the term low byte because that's the term that David Malone used in his paper, the paper that I was referring to before. Essentially, for low byte addresses, what you do is you set the interface ID to all 0, not because you want to do that, but that's the easy way to go. So in those cases, the search space will be either 8 bits or 16 bits. There are other variants of these low byte addresses. For example, there are some people that rather than changing or setting the lowest order 8 bits, they set the low order 16 bits or the second 16-bit word starting from the right. But essentially, the search space is very, very reduced when compared to the original 64 bits. Of course, the bottom line here is that we started from the assumption that the search space for finding a live host is 64 bits, and then we end up finding that actually the V6 addresses do have patterns, and when we take like a closer look at each of those patterns, we find that the search space can be greatly reduced. I'm going to talk a little bit now about some industry mitigations for host scanning or for address scanning attacks. Essentially, the only vendor that produced some kind of mitigation for this kind of address scanning attacks was Microsoft. And if you look at their V6 implementation, that's probably just the only thing that they got right. So that's why it's very important to discuss it here. And essentially, what they do is they select or they replace those addresses that are based on the MAC addresses with a random number. The actual specific algorithm is specified in RFC 4941. Essentially, it's a random number that they generate when you install the system, and once you do that, that number is fixed. So the idea is that since they set the interface ID to a random number, now the addresses that are configuring Windows systems, they don't follow any patterns anymore. So you couldn't take advantage of any of the patterns that we were discussing before, except, of course, if one of those systems was manually configured and you were to use low byte addresses or whatever. Certainly, this approach that Microsoft followed is much better than those addresses that are based on IEEE identifiers, but they are still not as good as they could be. For example, they still allow host tracking, and we will talk a little bit about that later. Okay, so some sorts of remote address scanning attacks, and I don't just say scanning attacks because there's a huge difference between scanning a network, scanning a remote network versus scanning a local network. Scanning a local network is a module for some tricks trivial, whereas scanning a remote network is a completely different problem. From my perspective, the B6 host scanning attacks are feasible. Of course, they are typically harder than the B4 counterpart. Actually, if you follow operations mailing lists such as Nano and so on, quite a few times they have been reported and seen in the wild. Of course, you might argue that they require more intelligence when compared to their B4 counterpart. In IPv4, the problem scale is so small that you can get away with doing like a pull job, which means sweeping the entire address space, whereas in the case of B6, you really need to do something clever or else your scanning attacks are not going to be feasible. In any case, it's possible to make these address scanning attacks unfeasible, and in the next few slides we will discuss some proposals that we took to the IETF to actually mitigate this problem. Aside from that, I personally think that there are going to be many other host scanning vectors that will probably be explored by attackers. There are many things that could be done. For example, trying to leverage application layer protocols. That could be from fetching torrent files from the internet and getting the addresses from there, taking a look at email archives and learning the addresses from there, and many other different vectors. So far, of course, they have not been explored for before because sweeping the address space was the low-hanging fruit. But with B6, even if we get to mitigate the typical address sweeping attacks, my take is that those alternative host scanning strategies will be explored. A couple of thoughts about the implications of B6 addressing on privacy. Essentially, I was mentioning before that the default way or default mechanism for selecting the interface ID is to embed the MAC address. That means that no matter which network you move to, your interface ID is going to remain constant because, of course, your MAC address is not going to change. Even in the case of Windows systems, that I said that when you bootstrap or when you install the system, they kind of like select a random interface ID. They use the same interface ID as you move from one network to another. So if you think about this a little bit, for example, if you assume that you have this interface ID over here, in which you have 111, 222, and so on, maybe you connect to the first network and you get this address 2001 DB8:1 and so on, and you can see that you have your interface ID here in red. And now let's assume that your host moves to a second or to a different network, which of course has a different prefix. Well, of course the prefix will change because you have moved from one network to another, but the interface ID will be the same. So let's now think for a second, and let's say that you operate a website and now you get a connection from the first address, okay, this one. and now sometime later you get a different connection from this other address, okay? Now, since the interface ID is the same and that value is supposed to be globally unique, then you can tell that the two addresses, even when being in different networks, are exactly the same host, okay? So that means that the interface ID is leaking out your privacy, it's leaking out your identity. So, what things have been implemented out there for mitigating this privacy issue? Well, when the IDF realized about this problem, a few years ago, there was RFC 4941 that was published. Essentially what this RFC says is that in addition to the traditional Slack addresses, you should generate a temporary address, or privacy or temporary address, in which essentially what you do is you produce a random interface ID. And these addresses are generated in addition to the traditional Slack addresses that you have. And the basic idea is that the traditional addresses will be stable. Of course, you don't change those addresses over time. Whereas the privacy addresses, of course, do change over time. So you use the stable addresses for server-like functions, like getting incoming connections, whereas you would use the privacy or temporary addresses for outgoing connections, which means for performing client-like functions. So some problems related with privacy addresses, first of all, is that they are difficult to manage. So for example, if you're operating a network, and for example, in the IPv4 world, it's typical that if you, for example, you find that there was this system that was infected and was trying to infect or attack other systems in your network, so you find the log and you say, okay, this system has been infected, we should go and fix disconnected or whatever. Well, now if you have the addresses changing over time, then you don't know which system was using which address at which point in time. So that's why I'm saying that these addresses are difficult to manage. And by default, there is no single place in the network that keeps track, or single system in the network that keeps track of which system was using which address. As a side comment, and I will provide a link later, we actually produced a daemon to actually keep track of the addresses. And that was in response to requests from the operational community that they said that they were interested in using these addresses, but they had no way to actually track them. When it comes to security problems, of course, these addresses do not mitigate host scanning or address scanning attacks, because you are still, these addresses are generated in addition to the permanent ones, and also they do not mitigate host tracking completely, because since you still have the stable addresses there, an attacker could, for example, send root packets to different networks to try to find out whether your system is in any of those target networks. So this is the proposal that we took to the IETF to mitigate both the host scanning and the address scanning and the privacy issues. When trying to come up with a solution, we started analyzing what are the types of addresses that we currently have. And we categorize these addresses into stable and temporary. Of course, stable, you don't change them over time. Temporary, you do change them over time. And also in the categories of predictable and unpredictable. So if you think about the addresses that include MAC addresses in the interface ID, they are both stable and predictable. You don't change them over time. And since, of course, the MAC addresses do have patterns, they are predictable. Then if you think about the privacy addresses, they are both temporary and unpredictable. So what we try to do is to come up with a proposal that could offer stable addresses but that were unpredictable. So they were easy to manage, but they didn't follow any kind of patterns, so that they were difficult to scan. This is the scheme that we came up with. Essentially, well, the name of the document name that you find there is the IETF document that documents our proposal. Essentially, the idea is that you would generate the interface ID as a result of a pseudo-random function, could be a hash, and you compute that hash over the prefix. The interface index, typically the interface index is a small number that identifies each of the network interface cards that you have. So it could be 0, 1, 2, and so on. The network ID, which could be, for example, for wireless networks, an SSID, and a secret key, which is of course secret. Okay? And of course, we assume that F is a cryptographically secure function. Now, of course, if you look at this function, as long as each of the parameters remains constant, of course, the result of the function is going to remain constant. Okay? And as soon as you vary or you change one of the parameters of this function, the result is going to change. Now, if you think about this, when you move from one network to another, the prefix will change, okay? The interface index will usually remain the same. The network ID will typically change. For example, if you are connected to a wireless network and the SSID changes, and the secret key will remain constant, okay? So the thing is, you are connected to one network, all of the parameters are constant, you move to a different network, now at least the prefix will change, okay? So the result of F will be different, and now if you move back to the original network, of course you get the original address that you had on that network. So the result of this proposal essentially is that you get addresses that are constant within each network. So every time you come back to the same network, you get exactly the same address. But when you move to one network to another, that interface ID changes and you get a different address. That means that we kind of like get the benefits from both worlds. So within a single network, you get a constant address, which is of course easy to manage. But now when you move from one network to another, your interface ID changes, and now you can no longer be traced. This document was already accepted by the relevant working group of the ITF 6 months, and hopefully it will get published as an RFC, hopefully this year or maybe if not next year. Okay, a couple of comments about fragmentation and reassembly. Essentially, in IPv6, all of the support for fragmentation has been removed from the base IPv6 header, and every support that you need for fragmentation is included in an extension header. So this is the format of the corresponding extension header, the fragmentation header, which of course contains essentially the same kind of stuff that you have for fragmentation in the IPv4 world. So you need a fragment offset that tells you the offset in the original packet of this particular fragment. You have an M bit that tells you whether there are more fragments following or not, and you have an identification bit with an identification field which is used to identify fragments that correspond to the same packet. So, for example, if you think about the fragment identification, its security implications, for example, when you use a predictable fragment ID, are completely known, has been known for ages. We know that from the IPv4 world, idle scanning, DOS attacks, etc., etc. And in the case of V6, actually the problem is a little bit exacerbated because we will probably have increased use of fragmentation as a result of protocols that, for example, use UDP, such as DNS, and as a result of the additional information that needs to be transferred as a result of DNSSEC, the larger addresses, there's probably going to be increased use of fragmentation. Now, you would argue that since we hit this problem like more than 10 years ago in IPv4, this problem was already solved for IPv6. So we actually produced tools and assessed different implementations, for example, when it comes to how they generate the fragment IDs, and these are the results that we got. For example, Solaris, Windows, and Linux use to use predictable fragment IDs. In the case of Linux and Solaris, they produce patches when we reported this to them. In the case of Windows, I never got them to understand what was the problem, so I essentially gave up with them. So if you try this kind of thing with Windows, you will find out that they are still using predictable fragment IDs selected from a global counter. Of course, the solution to this problem is, at least in principle, is kind of like trivial. You should avoid predictable fragment IDs. We have a document at the ITF, the one that is mentioned in this slide. In the current version, we discuss different possible algorithms to select the fragment ID. I mean, in theory, it's simpler than it is in actual practice. So if you want to get into the details, I recommend going to that document. But bottom line is, don't use predictable fragment IDs. Another topic is that of fragment reassembly. Of course, we know from the IPv4 world that when you allow overlapping fragments, that can be leveraged to evade intrusion detection systems. That has been known for years, and unfortunately, we had the same problem with IPv6. A couple of years ago, there was an RFC 5722 that was published, which essentially forbids the use of overlapping fragments. And from the assessment that we did of different implementations, you could argue that most current implementations already forbid these overlapping fragments. However, there are some, for example, the latest release of Debian, because of the version of the kernel that they use, they are still allowing these overlapping fragments. And in our blog, we have a table of an assessment that we did of different implementations when it comes to this issue. Kind of like a similar problem has to do with what we call IPv6 atomic fragments, and to put it in to kind of like summarize this, the specifications require that if you get an ICMP version 6 packet to big error message, analogous to the fragmentation needed by the F bit set from the IPv4 wall, you are not required to, if the advertised MTU is smaller than 1280, you are not required to actually reduce the size of your packets, but you must include a fragment header in the subsequent packets that you send. Now the thing is that you have the original packet here, and below that you get essentially what we call an atomic fragment, which means that you have the whole contents of the original packet, except for the fact that it includes a fragment header. So you don't really need to reassemble these atomic packets with any other fragment, because everything or all of the contents of the original packet are within that fragment. It's a first fragment and last fragment at the same time. So what is the problem that you find with this atomic fragment is that many implementations were essentially mixing the atomic fragments with all other fragments, other real fragments that they had in the fragment reassembly queue. Of course, that meant that you could easily exploit or perform fragmentation-based attacks against traffic that was otherwise not using fragmentation. The way to do that was very simple: just fire an ICMP version 6 packet to bit that will trigger the use of atomic fragments, and once that connection is using atomic fragments, then you can fire fragments to perform any IPv6 fragmentation-based attack. So we sent the proposal to the IETF. It's very straightforward. Since atomic fragments are atomic, you have everything you need in the same fragment. Essentially, you shouldn't mix the atomic fragments with regular fragments that you might have in your fragment reassembly queue. This is an assessment that we did for different implementations. The ones that you have marked in red below are implementations that mix the atomic fragments with regular traffic. The ones that say yes are the ones that implement this improved processing, which means that even if they have fragments queued in the fragment reassembly queue, they will not mix the atomic fragments with the regular fragments. A few of these, for example, not Linux, OpenBSD, and I don't recall correctly Solaris, but OpenBSD patched this in response to our publication, and hopefully there will be others that will follow. Couple of comments about IPv6 first hop security. Essentially, first hop security is the mechanism and policy that you can employ and deploy on your local network to address security issues. One of the main problems that we have is that we don't have feature parity with IPv4. For example, in before we have tools such as ArtWatch that allow you to track ARP-based attacks. We don't have the same thing in v6, or actually we do have tools, but it's easy to circumvent those tools. And also in IPv4 we have mechanisms such as DHCP snooping, but we don't have parity with that in IPv6. So what's the fundamental problem with first hop security? If you think about v6 traffic, the protocols that are used, for example, for other resolution, such as neighbor discovery, which is the equivalent of ARP in the IPv6 world, operates on top of IPv6, which means that it can use extension headers, it can use fragmentation, and so on. So you could have, for example, this original packet here, okay? And an attacker, of course, in order to try to avoid or circumvent security devices, he could include destination options headers or other extension headers and then fragment the packet. And what you actually get on the network are these two fragments over here, which of course are essentially impossible to police in a stateless way. And since you should enforce these policies at layer 2, of course it doesn't make any sense to actually try to, for example, reassemble and forward. You cannot actually do that. So what we did, we took a proposal to the IETF to ban the use of fragmentation for neighbor discovery. In practice, it's not needed, and it's not used or needed for any legitimate scenarios, but it causes trouble when you want to actually enforce security policies. This has been already accepted by the 6-man working group, and hopefully it will be published as an RFC shortly. This means that when it comes to neighbor discovery traffic, we won't have such packets use fragmentation, so it will become trivial to actually filter those packets or monitor them and so on. A security device that was standardized and actually implemented years ago was known or is known as router advertisement guard. Essentially, this is analogous to DHCP snooping. If you have a managed switch with different ports, you can tell the device, okay, I want you to only allow router advertisement messages on this specific port, and if you get router advertisement messages on any of the other ports, you should block them. This is what we know from the B4 wall as, for example, DHCP snooping. The ITF produced 2 RFCs that standardizes this. Cisco implemented this and sold this to customers, but in practice it's trivial to circumvent. You just need to include some extension header in the middle, and that's all that is needed to actually evade this device. We took our proposal to the ITF. It is this document that is mentioned in this slide, which essentially describes the problem of how you can evade the current implementations of router advertisement guard, and it also provides mitigation for that. Again, we're not just pointing fingers at where the problems are, but for each of these issues we actually produce mitigations. With this change in mind, with this change in place, router advertisement guard could only be evaded with overlapping fragments, but as I mentioned before, most current implementations already ban those packets. This is already a document that is in the RFC editor queue, which means that it should be published as an RFC soon. Few comments about B6 firewalling. As I said before, essentially from the specifications point of view, you can have packets that have any number of extension headers, which is this stuff that you see here, okay? And not only can they have multiple extension headers, but they can also be fragmented. So in the network, at least in theory, you could get these packets that you're seeing in this slide. That essentially means that you cannot perform any kind of stateless filtering. The only way in which you could do IPv6 packet filtering with this thing in mind is to actually reassemble and then filter and then forward, okay? So again, for this case, what we took to the IDF was a proposal that essentially requires that you can include as many extension headers as you want, but the whole IPv6 header chain should be contained in the first fragment, which means that the fragment with an offset of 0 should have all the extension headers up to the upper layer header in the first fragment, okay? And that means that when you receive a fragment, if it's the first one, you know for sure you will have for sure all the information that you need to apply a filtering policy. This is just a single aspect when it comes to IPv6 firewalls. There are even more basic questions to answer. For example, nobody knows what's an IPv6 firewall. So if you are an operator and, for example, are asking vendors, okay, do you have an IPv6 firewall? Well, there are many vendors that they do have IPv6 firewalls, but then when it comes to the features, usually they are far from what they support for IPv4. There are other cases in which, for example, they might have similar functionality in both protocols, but they implement the B4 part in hardware, and they implement the IPv6 functionality in software, etc., etc. I personally think that there is a lot of work to do in this area, so that you can have some idea of what we're talking about when we talk about IPv6 firewalling. From my personal perspective, probably one of the reasons for which we don't have any of these documents at the ITF is because essentially for the ITF, firewalls have been considered evil for more than 20 years, or forever if you want, and that's why there essentially has been no work in the area of firewalls, not only B6 but also B4. A couple of comments about B6 implications on IPv4 networks, and typically the reaction here is, well, if my network is B4 only, why should I care about B6? Well, the answer here is that most networks are not really B4 only, because many, if not most of the devices that you have on that network, they have B6 support of some form. That could be dual stack support, that could be support for transition technologies, and so on. There is lots of work that we did in this area, such as, for example, how you should filter different transition technologies. But I tried to include in this slide something that we came up with maybe a month ago, or not more than that, which is about VPN leakages. And this is something that is so stupid, but it's actually also so practical and so true. So let's say that you go and connect to an insecure network, let's say a conference network or whatever. What you typically do is you establish a VPN with your office, with your home or whatever, so that you securely tunnel all of your traffic to a place which is supposed to be a little bit more secure. Typically, the VPN device or software that you use is IPv4 only, okay? So that software doesn't support IPv6. Now, what happens? So, scenario one, let's say that you are connecting to a network that supports both V6 and V4 connectivity. Now, when you connect to that network, you get both V4 and V6 addressing. And if the destination that you are connecting to is V6 enabled, that might mean that your traffic is not going to go through your VPN, but it's going to go in the clear over the V6 connection. And that's just a legitimate case. That could happen if I go, let's say, to the IETF network, which supports dual stack. Of course, this can be actually forced or triggered by an attacker. So I'm connected to this network, essentially I throw router advertisement packets, and I tell all the local systems that I'm an IPv6 enabled DNS server. So when you try to visit a site or whatever, I will give you IPv6 addresses for those sites. And since your VPN software only supports IPv4, then you will use the native network, which is the only V6 connectivity that you have. Again, you thought that your traffic was going through the VPN, which was secure, encrypted, and so on, and now your traffic is going in the clear on a completely different network. It is not unusual that when you discuss this stuff with some people in the security community, there's always someone that says, "Oh, we knew that already," but and of course, this was no exception. So there was a guy that at least said that he knew this stuff already, but the thing is that if you look at both open source implementation for VPN and also at commercial ones, they are still vulnerable to this kind of stuff. So bottom line, get this in mind if you're using a VPN, or else disable V6 support when you're using your VPN software, because your traffic might be going out of your VPN. Tools, people like tools. So when it comes to V6, the only attack suite that has been there for ages was THC's IPv6 attack toolkit. For many years, I have not counted them. So this is the link to where you can find this tool. And we produce a different, brand new, you call that security assessment toolkit, troubleshooting toolkit, whatever you want to call it. The toolkit that we produce runs on Linux, BSDs, and macOS. We tried hard to make the toolkit portable. I learned that it's not really an attack toolkit in the sense that if you try to run the tools without any V6 knowledge, you won't get anything, except like a help message telling you how to set the different options. So from my perspective, it's a toolkit that is useful if you have all your attacks or potential issues in your head, and you just need software to actually convey those packets in the network. Okay? Again, if you know the basic stuff, you probably will find this toolkit useful. If you just want to run a script to do something, like DOS something, I don't think you will find the toolkit useful. This is the URL for the toolkit. We have the tarball and so on. And this is also the GitHub page where you can get the latest version of the toolkit. These are the tools that are covered or that are included in our toolkit. Scan6, a tool for performing, at the time, only local network scan attacks. A tool for performing fragmentation-related attacks. A tool for playing with TCP, like doing, for example, TCP SYN flutes, but over IPv6. Different tools for playing with IPv6 neighbor discovery, etc., etc. And also tools, for example, for playing with IPv6 jumbograms, sending ICMP error messages, etc., etc. I don't know if I have it here, but okay. This is just one of the tools that we have. It's the local scanner. And this should be, I mean, this is pretty simple stuff, but this is just to show that even if you think that you are not running V6 because the network is V4 only, these are the IPv6 addresses of systems that are connected to the BruCON network, okay? There are lots of things to be added to the toolkit, okay? And well, there's somebody that either is providing V6 connectivity or that has performed an IPv6 related attack, because like 10 minutes ago you didn't have any 2001 prefix here, okay? Again, there are lots of stuff to see in the toolkit. I was just trying to show one of the tools in action, and there is much more to implement in those tools. Some conclusions, essentially, I learned that many of the vulnerabilities that we know from the IPv4 world have been re-implemented in IPv6. There are probably different takes on why that happened. For example, we didn't learn the lesson from IPv4. Maybe it was different people working on the V6 code as opposed to the V4 code, and that's true. If you look at the commits on the IPv4 code when compared to the V6 code, it's different people. You could also argue that the IDF specification could have been more straightforward in terms of how to implement the IPv6 protocol more securely. And probably the reason for which we have these kind of issues in V6 implementations is a combination of all of the above factors. There is still lots of work to do on V6 security, building tools, testing, implementations, etc., etc. And from my perspective, the bottom line is that we need IPv6. Sooner or later, we will have to deploy it because we need additional IP addresses. So we should not only work to actually point out the problems, but also try to do some work to improve the current state of affairs. As a side comment, and if you want a politically incorrect comment, if you think about the maturity of IPv6 implementations, from my perspective, we are kind of like in the same place we were with IPv4 in the 90s. So you still find very stupid bugs in V6 implementation that shouldn't be there. Any questions? Yeah.
Got time for a couple of questions, so if I don't fall on the stairs.
Okay, so the question is, do you know anything about that if Microsoft had changed their mind and they plan to start to support secure neighborhood discovery protocol?
No. As far as I know, they don't have any plans to support SEN. I will also add that one of the problems with SEN, that's my personal perspective, is that it's a lot of burden to solve too little, in the sense that you still have so many pieces of the network insecure, such as the DNS, that at this point in time, it doesn't provide much of a return of investment to actually deploy SEN. SEN requires a PKI, and for most people, that of setting up a PKI is too much of a problem. So even when it comes to, for example, open source projects, I think that many of them didn't have a SEN implementation at all. That has changed a little bit, but for example, I think that 3 years ago, the only thing that you had for BSDs was a Java implementation of SEN, which is cool for actually testing the protocol, but it's not really in production.
Yeah, about the super cookie addresses, isn't it enough to have the priority of your addresses set to the random addresses that you change over time, and then use your MAC-based or whatever DHCP-based address as a managed address?
Sorry?
You have a random address, you can create it, and you can set a priority for the random address higher than your managed DHCP-based or MAC address-based address. Isn't that enough for privacy?
Well, not really. I could give you a scenario. Let's say that I learned what your interface ID is, okay? I mean, of course, that mitigates the problem to a large extent, okay? But host tracking is still possible. Let's just say, for example, that I know your interface ID for the stable address, okay? And for some reason, I know that you will be connected at least in one of these 100 networks, okay? So one thing that I could do is I could send a proof to that network to your stable address and see if you're there.
But I can put my managed addresses in a different subnet, or I can put my managed addresses in a firewall.
Well, but that is different. Well, but actually you couldn't or you shouldn't do that, but because the very reason for which you have a stable address is so that you can get incoming connections. So if you're going to firewall your stable address, just don't use the stable address, just use the temporary one.
Managed addresses you usually use for your internal management. And your addresses, your random addresses, you should use for your internet connectivity. You don't need connections back.
Well, the reason for which when the ITF standardized RFC 4941 and they mandated that the privacy addresses were generated in addition to the stable ones, was so that you could get incoming connections. That's their proposal, at least. Okay?
That is an added feature. Good,
okay.
Thanks.
I think if there's no more questions, we'll call it a day or an evening or whatever you want to call it. Thanks so much, Miran.
Okay.
Great talk.
Thank you.
If everyone can make their way that way to beer and parties and dancing girls and dancing boys and whatever you prefer, I don't know. Bueller, Lisa. Craig Walding, you're a stacking up man. Could you take the top off? For me? For now?